So this is a small presentation about GCoE-ACE at IIT Dharwad. The center is working on Sustainable Development Goal number 7. The Sustainable Development Goal 7 is, there are 17 Sustainable Development Goals defined by United Nations. And goal number 7 is on affordable and clean energy. These goals we need to satisfy by 2030. Also, India has a plan to go for net zero emission as a target by 2070. And this was declared by our Prime Minister Narendra Modi ji in COP26 at Glasgow. Affordable and clean energy has a strong linkage with the climate action, that is also Sustainable Development Goal number 13. And you could see that there is linkages to other goals. Any development in affordable and clean energy sector can create a multiplier effects in economic progress, healthcare, and education, as well as environment. The center has been inaugurated at IIT Dharwad on 20th of January 2022 by former PSA, Professor K. Vijayaraghavan. The center is supported strongly by the Principal Scientific Advisor, Government of India, Selco Foundation, Honeywell, and Infineon. Center is committed to provide laboratory facilities, upskilling programs. So we are going to start the upskilling programs from the October month. Research and development activities, mainly in power electronics domain, outreach and talk series. Currently, 3 is a talk series. Hackathon and challenges, innovation, incubation support, as well as grassroots level implementation and field level experiences and mentorship. So these are the equipments that we have currently. Equipments at the center are categorized as test and measurement equipment, fabrication and prototyping lab, skill development lab, R&D lab in power electronics, as well as we are coming up with a model village. You are free to collaborate with us, come and use these facilities. So these are the other facilities. There is a power hardware in the loop, which we call HIL simulator platform with real-time controller prototyping. So this is for power electronics and R&D equipment. So you are also free to come and use this facility. The center has been inviting a problem statements, articulation and detailing. So basically it has a Google form which asks you different questions, and what we are expected is a problem statement where a definition of problem statement for 200 words. This is available on our website, this invitation, and you can participate anytime. Currently, there are 30 plus problem statements already been captured through online and offline events. There is another innovation challenge from the center is currently on. Today is the last date for the first call. We are going to release the second call from tomorrow. The second call for the Catalyze Tech 2022, that is inviting the innovators and entrepreneurs, would be having a deadline of 20th of October. This is to make social innovations in the sector of energy, clean energy, and we are open for innovative ideas and supporting that innovative ideas. So if you have any queries, you reach out to us. Our email address was given in the slide number 1. Yeah, so you can reach out to us at fic.ace@iitdh.ac.in or office.ace@iitdh.ac.in. So thank you. This is a small introduction about the center. Now I will give the introduction of our speaker today. Just stop sharing. Okay, so now I will introduce the guest speaker today before inviting him to begin his talk titled Nanosystems and Architectures for Enhanced Energy Storage. Professor K.R.V. Subramanian is working as a professor with mechanical engineering and also as a research coordinator at Ramaiah Institute of Technology, MSRIT, Bangalore. He did his Bachelor of Engineering and Master of Engineering degrees from NIT Trichy and IISc Bangalore, respectively. He earned his Ph.D. in Nanotechnology from Cambridge University, UK in 2006. He carried out His postdoctoral research at the University of Illinois at Urbana Champaign, USA from 2006 to 2008. He has worked for prestigious academic institutes and organizations such as Amrita University, Tata Motors and Larsen and Toubro. He has a total of 27 years of work experience, published 93 international journal papers, edited 4 books, 65 conference presentations, and has 14 patents to his credit. He has received outstanding reviewer awards from RSC Advances, Journal of Power Sources, Materials Letters, Materials Chemistry and Physics, Materials Research Express. He has completed externally funded projects from MNRE, DST, CSIR, CIRI, NIH USA, as well as he is a member of Royal Society of Chemistry UK and Fellow of Cambridge Commonwealth Society UK. He is a recipient of Commonwealth Trust Scholarship. His current research interests are energy storage, solar technology, thermodynamics, carbon nanomaterials, nanofluids, thermal barrier materials, and cancer nanotechnology. I request Professor Subramanian to please share the screen and start the presentation. I will switch on the question and answer box. Please free to put your question answers in the QA box.
Yeah, thank you, Professor Dheeraj. Thank you very much for the kind introduction.
Thank you, sir.
Thank you, and also for inviting me for this invited talk with the GOC, the Global Center of Excellence. So I will now share my screen. Are you able to see the presentation?
Yes, yes. You can go on a full screen mode, sir, and then you can click on that hide.
Yeah, sure.
Yes.
Yeah. Okay. So good morning, everybody. The topic of today's talk is nanosystems and architectures for enhanced energy storage. So this is the outline of my talk. I will give a brief about energy storage introduction, current challenges in energy storage, advantages of nano and green materials in energy storage, and I will also detail my previous work and current work, which includes integrated solar and energy storage, conducting polymer storage structures, graphene and carbon nanotube based systems, graphene based flow systems, nanofluid electrolyte systems, sodium ion and lithium ion chemistry, green materials, nano architectures for sensing and storage, and development of solar perovskite nanomaterials for storage integration. And I will also give a brief on the intellectual property and product development activities, and then finally conclude and take the question and answers. So let us introduce the audience to a little bit of energy storage. So energy storage is a key aspect in the smooth functioning of numerous gadgets that aid easy maneuvering through modern life. And one of the key components is supercapacitors that store energy periodically, and they have emerged as potential inventions for which mechanical flexibility is an absolute requirement for their future applications. Energy storage devices which can deliver stored energy for later usage have been highly sought after for the uninterrupted functioning of the various gadgets required for everyday work. So there are various associated devices in this category, which include capacitors, batteries, fuel cells, etc. And the recent descendant of this family is supercapacitors, which are capable of delivering high power densities and reasonably good energy density, and they are creating new trends. And the recent works are focusing on the development of flexible supercapacitors. So this has a combination of mechanical flexibility and high electrical output, and this makes the devices suitable for applications in wearable electronics, wearable power supply devices, regenerative braking in motor vehicles, etc. And the devices store energy predominantly by reversible Faraday redox reactions at the interface, of an electrolyte and electrode material. Electrode material is made up of the active material. There is also some contribution from the electric double layer formation, which may contribute to the overall energy storage mechanism, depending on the type of materials used and the structure of the device. These devices demonstrate exceptional endurance when tested under repeated mechanical deformation, such as twisting, bending, and stretching to severe degrees. So what are the current challenges in this arena? Now, most of the researchers and especially people who are working on this area, they have to have the holy grail of high specific capacitance, high energy density, high power density, long cycle life, scalability, ease in packaging, and flexibility with low cost. And the specific capacitance of the electrode and other electrochemical properties has to be retained, especially when you bend the device to extreme degrees. And this indicates the self-healing nature of the composite that form the electrode. And researchers are also looking at hybrid nature of the electrode. They are also studying the synergistic interactions between various nano constituents of electrode and electrolyte. They are also concentrating on faster charge transfer kinetics and lowering of the energy activation barriers. And most of the research work is supplemented with a good impedance spectroscopy behavior, which leads to low charge transfer and contact resistance. What are the advantages of nano and green materials? So most of these materials, they have low cost, they are environmentally friendly and easily available. They are the ideal building block for advanced functional materials. They have the advantages of high surface area, tunable porous structure, and excellent thermal stability. The fibrous structure can enhance ionic conductivity of the composite electrode, and they also have the self-healing nature of the electrode and the required structural and morphological integrity. Let us go to my work. I start with my previous work and then I will progressively go on to my current work. So one of the first concepts that I studied about more than 10 years before is the integrated solar energy storage. So as you can see, if you combine a solar cell with a capacitor, you can see that the output can be drawn only from the solar cell or only from the capacitor, or it can be drawn from both the solar cell and the capacitor. So the diagram which is shown below shows a integrated structure where you have anodized titanium plate. So you can see the nanotubes which are there on either side of the plate. So on one half of the plate, the solar structure is built up. So what is built up is actually a dye-sensitized solar cell, where the dye is coated on the TiO2 nanotubes, and then you have the electrolyte, the redox electrolyte, and then you have the counter electrode, which is the platinum coated ITO. So the solar cell functions in the DSCC mechanism. But you can also see that on the other side of the titanium plate, the titania nanotubes are extending on both sides. And there is a thin layer of zirconium dioxide, which is a dielectric material. So the other side of the titanium plate functions like a capacitor, which can store charge. And because it shares a common interface, the charges can flow seamlessly from the solar cell to the capacitor. So this is a integrated solar and energy storage realized through double anodization of the titanium plate. So this shows a high magnification SEM image. You can see that this is the titanium plate on the figure A. You can see that nanotubes are growing on either sides. You can see a forest of nanotubes, and the same nanotubes are also shown in a high magnification image in figure B. So you can see that all the tubules are growing out of the surface, right? These are all titanium dioxide nanotubules. So we have carried out, the characterization of the solar cell and the storage separately. So you can see that figure A shows the IV curve of the solar cell. So you can see that current and voltage is varying with a typical knee voltage, which is the typical of the IV behavior of solar cell. Now the figure B shows the storage behavior which is nothing but galvanostatic voltage versus time. So you can see that voltage is rising to a maximum value in the charge sequence, then it is discharging, and then this cycle can be repeated for as many cycles as possible. So we got a capacitance of 140 millifarads per centimeter square. So you can very well see that it's a very small structure, and we are having titanium dioxide nanotubes. So even realizing 140 millifarads per centimeter square is a very good value from this storage structure. Now coming to the integration, suppose you shine the light, the natural light or the artificial light on the dye-sensitized solar cell. So you can see the figure A. It's a voltage time plot. So you can see that when the light is turned on the solar cell, the voltage is increasing, right? And it goes to a maximum value. And you can see that the voltage remains constant when the light illumination is on, right? And even after the light is turned off, the voltage does not decay. So that means, whatever the solar energy is shown on the DSSC, the charges have been stored in the die, and they have been, responsible for the open circuit voltage. And only when you apply a discharging current at about 2000 seconds, only then the discharge is triggered. You can see that the discharge has started around 1500 seconds and goes on up to 4000 seconds. So this is on the figure B shows the current time behavior of the solar cell. You can see that, as the light is shining, the current is increasing and then it reaches the saturation value. So this is the proof of concept that, you can simultaneously shine the light, the solar light, as well as charge in the same structure. So this was a very, good proof of concept, which was also published in Progress in Photovoltaics. So then going ahead, we try to scale up this concept. So we made a solar cell on a larger substrate, and we made storage devices which includes supercapacitors and batteries. And you have to couple them, right? So you need an integrated circuit. So this is what is, the layout of the integrating circuit. So you can actually have a small thin panel. On one side you have the solar component, on the other side you have the storage component, and the charges are seamlessly flowing from the solar component to the storage component. So this can be used even when the sun is shining and even in the dark condition, because the storage mechanism can be used even when the solar light is not shining. So this shows the complete integrated structure on the left hand side. So to do this, we had to do a lot of research. I had to investigate separately on the solar cell. So solar cell, as you know, it has an anode, especially the dye-sensitized solar cell, it has anode, cathode. So we looked at nanostructured titania with graphene, and we also looked at P.PSS, which is a conducting polymer on the cathode side. And on the supercapacitor hybrid battery, we had to devise a different electrode. So we looked at structures like manganese dioxide and nickel oxide nanostructures. We looked at lithium manganese oxide with carbon. We looked at lithium iron phosphate and lithium sulfide, lithium sulfur, which were new concepts. And then the integrating electronics, which will combine the solar cell and the battery components, right? So that is what is shown in the bottom right hand side, where you can see a very compact panel. This has both the solar and the storage component on the same panel. So this is a brief on the dye sensitized solar cell. So we have the sensitizing dye, which is the ruthenium N719 dye or the N3 dye, and titanium nanoparticles are nothing but the active layer, which will transport the charges. And we also have an electrolyte, which is the redox electrolyte, which is basically iodide and triiodide ionic liquid. So coming to conducting polymer energy storage. So the first work we undertook was on graphene polypyrrole. So this was published in Chemical Communication. So you can see all these images, SEM images, high magnification SEM images. So initially the conducting polymer was electropolymerized, right? So what you do is you take polypyrrole, which is the conducting polymer, and then we electropolymerize onto a substrate using applied voltage, right? And on top of the, you can see the polymeric nanotubules in the part F of the figure. On top of that, we have deposited the graphene by electrophoretic deposition. So you can see C and E, that is the combined structure of the graphene and the polypyrrole, right? So these are all, very, very tiny structures. And the graphene, what we deposited had a distinct Raman signature as shown by the graph below. So these are the electrochemical characterizations of the composite structure. So you can see part A. You can see that if you use graphene alone, as shown by the red curve, this is the CV curve. This is the cyclic voltagram curve. If you see the red graph alone, the area under the curve is very less. That is primarily because graphene has an electric double layer capacitance only. And then we have the polypyrrole, which is shown by the black curve. If you combine these two, you can see the dramatic improvement in the area under the CV curve. That is shown by the blue curve, which is graphene plus polypyrrole, right? So we have tested this cyclic voltagrams under different scan rates, and we have also tested for different times of polymerization. So we have found that 1500 seconds is the optimum time for polymerization, and you can also see that we have tested the cycling ability of this composite. So the kind of capacitance we got was 1510 farad per gram, area capacitance of 151 millifarad per centimeter square, and volume capacitance of 151 farad per centimeter cube at 10 millivolt per second scan rate. Coming to graphene-based storage systems, one of the interesting systems we studied was graphene cobalt hydroxide. So cobalt hydroxide is a very unique nano material in that it has got a layered structure, right? So what we have done is we have taken porous beta cobalt hydroxide nanoflake thin films, and they were prepared by galvanostatic electrochemical deposition on stainless steel substrate. And the starting material was cobalt chloride hexahydrate, and we could get a capacitance of 496 farad per gram at a current density of 4.2 ampere per gram, and electrolyte used was potassium hydroxide. So what we have done is we have sequentially deposited the composites of beta cobalt hydroxide with graphene, and we have found that the performance maximizes when the number of sequential layers is 2. So I will show you some subsequent graphs which actually shows the behavior. And we have also got a power density of 4.6 kilowatt per kg. And we also got a specific capacitance of 568 farad per gram for the 2 sequential layered composite samples. So these are some high magnification SEM images of the composite structure. So you can see that the cobalt hydroxide is in the form of a flaky form, and on top of that we deposit the graphene. So we were able to get a porous structure and a porous multi-layered structure. And this was published in Energy Technology in 2013. So this shows the cyclic behavior under cyclic photometry. So you can see that even after 1000 cycles, it is almost, it has very good fidelity. And we also carried out TEM of the composite structure and as well as SAED. So you can see that, it has got a very, very flaky structure and a layered structure. And this shows the behavior under different layers. So you can see that on the left hand side of the diagram, we have 1 layer, 2 layer, 3 layers. So you can see that the 1 layer structure has got very low area. As we go to 2 layers, it increases, and 3 layers, it even increases further. And you can also see the we have even gone up to 4 layers. So you can see that the area under the curve is continuously increasing. So what I mean by 4 layers is you have cobalt hydroxide graphene, which is one layer. Then you have cobalt hydroxide graphene, second layer. Then you have cobalt and then cobalt hydroxide graphene, fourth layer. So this is how it works. So this shows, the dramatic change in the area under the CV curve. So this is, you can see that, the blue curve actually shows the graphene behavior, and the red curve shows the cobalt hydroxide behavior, and the combined behavior is shown by the black curve. So, you can see that there is a synergistic interaction between cobalt hydroxide and graphene. So let us go to the next system, which is exfoliated graphene-based storage, which was published in Renewable and Sustainable Energy. So what we have done is we have taken graphite and we have chemically exfoliated. Not only chemically, it is a combination of chemical exfoliation and mechanical exfoliation. So we have done ball milling, and we have also used a chemical exfoliating agent, which is 1-pyrene carboxylic acid. And we have done the liquid exfoliation in methanol and DMF. So these are the Raman spectra you can see on the left hand side and right hand side. The left hand side is on the methanol as a solvent, and the right hand side is using DMF as a solvent. So you can see the typical curves, the D curve, the 2D curve, the D band, 2D band, and the G band. So all these are seen in the Raman spectra. This is the SCM image of the exfoliated graphene. So you can see that it is in the form of a layered structure. This is the TEM image, high magnification of the exfoliated graphene. So you can clearly see two things. One thing is, the number of layers of graphene is very less, and also there is a good amount of transparency. So that shows that exfoliation has happened very well. And this is the XRD plot of the the graphene. So we have taken graphite, we have exfoliated for in methanol for 13 hours, 20 hours, and 30 hours. And you can see that the structure which has been exfoliated in methanol for 30 hours, it has developed a very good XRD structure as compared to the other plots. This is the electronic conductivity of the various exfoliated graphene. So you can see that graphite conductivity in Siemens per meter is only 1.4 into 10 raised to 3. If you go for 10 hours, which is N13, the conductivity increases to 1.93. If you go for 20 hours, it increases to 2.34, and if you go for 30 hours, it increases to almost 7 into 10 raised to 3. So that shows that the graphene is becoming more and more exfoliated and also pure. That is how it is able to retain its electrical conductivity property. And this shows the dramatic behavior in electrochemical studies. So this is a CV curve. So you can see that the graphite curve is almost minimal because it does not show much electrochemical response. Then if you go to the the 13 hours prepared sample in methanol, it has got a almost vanishing area under the curve. 20 hours is slightly better, but look at the 30 hours curve. It has increased dramatically. So that shows that if you prepare graphene very well through exfoliation, it can be used as a very good material for energy storage. Professor Dheeraj, everything is fine. Am I audible?
Yes, you are audible. Please
okay. Okay. So let us come to flow systems. This is something we have taken up after we studied the static systems. So one of the concepts is called as electrochemical flow capacitor. It's a new concept of energy storage mechanism, which has advantages of both batteries and supercapacitors. So it is a flow capacitor that has adopted the electrolyte flowing mechanism of flow batteries and the charge storage principle of electric double layer capacitors. So in the electrochemical flow capacitor, electrode material stores the ions from the electrolyte, and it stores charge like static EDLCs, but the electrode material is not coated on the electrode. It is in a flowable form. So that is the advantage of using the EFC. So we have investigated, electrochemical flow capacitor performance using graphene nanoplatelet based slurry, And we have also used the control material, which is graphite-based slurry. And the kind of performance we got was, if you take a graphene-based slurry in an intermittent flow capacitor, we got a capacitance of 64.5 farad and energy density of 14.3 watt hour per liter. And if you use it in a full flow device, then you get a capacitance of 1.08 farad. And we also saw that if you use ionic electrolyte, then we get energy density of 6 watt hour per kg. And this is much better than the graphite based slurry, which only gives about 2.2 watt hour per kg. So this is the structure which was made to construct the electrochemical flow device. So you can see that the flow cell is very simple. It has got the current collector and the electrode, and there is a separator in between. And then it is housed in the the center of the device, and it is connected to 4 peristaltic pumps, which drive the slurry from the container. So, for example, the flow of electrolyte into the cell and out of the cell is determined by the peristaltic pump. So, this device, it was a device made in the laboratory, and it was also published in Journal of Materials Chemistry. So, this is the chronoamperometry data what we got. Just one.
Hello. Professor Subramanian. Professor Ivankar, am I audible?
Yes, sir, you are audible.
Tim, right? We will wait for a couple of minutes. I'm in contact with him. So Professor is logging in again. Some power connection issue. Also, please feel free to post the questions in question answer box or a chat box. Professor Subramanian? Professor Subramanian, you are muted.
Am I audible?
Yes, you are audible now.
Yeah, I will just share it again.
Yes, please.
Yeah. Sorry, there was some.
No problem.
Yeah.
Yes, your screen is visible.
Yeah. So shall I continue?
Yes, please.
Yeah.
I think previous slide to this, I think.
Yeah. Right. Yeah.
This one. Yeah.
Yeah. So this was a device which was made, and it was used for testing the electrochemical flow cell. So you can look at the chronoamperometry curves, which is current versus time. So you can see that the commercial graphene is performing much better than graphite or in-house graphene. And similarly, you can also see the discharging behavior. So again, the graphite discharging is, it's not as good as if you take the commercial graphene or the in-house graphene. And this is the full flow device. So we had two kind of devices. One is intermittent flow and another one is full flow. So we can adjust the peristaltic pump to control the volume of flow into the cell, into the flow cell. So if you take a charging behavior of a full flow device, you can see that graphene is performing much better than graphite. Graphite is shown by the red line. And similarly, the discharging behavior is better for graphene as compared to graphite. And this is a cycling study, so we had carried out up to 130 cycles. So you can see that there is very good fidelity of the behavior. There is not much fade of the charging or the discharging. So next, going on to nanofluid electrolyte system. So one of the devices we are currently studying is a sodium ion supercapacitor. So the idea was, normally what is used in the sodium ion supercapacitor is sodium perchlorate, which is the normal electrolyte in propylene carbonate. So we modified that electrolyte with nanofluids of copper oxide and iron oxide in ethanol. And of course, the electrodes of the sodium ion devices are itself made up of nanomaterials like carbon nanotubes, sulfur, cellulose, activated carbon, etc. So we were able to get very good values from using nanofluids. So we got an energy density of 125 watt hour per kg, power density of 20 kilowatt per kg, and a current carrying capacity of 200 milliampere hours per gram. So these are comparable to some of the best values in literature. So these are the CV graphs, which are, the first one is for the base material. So we have used the perovskite material as the nano component in the cathode. So which is nothing but cesium sodium bismuth fluoride. And B and C show the behavior when we add copper oxide nanofluid. So you can see that the area under the curve is increased when we add the nanofluid into the electrolyte. So, and this graph shows when we add iron oxide into the nanofluid. So again, the area under the curve is considerably increased when compared to the base electrolyte. So these are some of the CM pictures of the electrodes, which consist of multi-wall carbon nanotubes. They consist of sulfur. They also consist of the perovskite material. So you can see that it is it's a composite material which is forming the electrode of the sodium battery. And the very good thing about nanotubes is, I'll just come to this in the subsequent in these slides. So, what was the reason for using multi-wall carbon nanotubes? So this was published in Materials Letters recently. So multi-wall carbon nanotubes has got a very open tubular structure, and it is very highly suited for sodium intercalation. So the theoretical inner diameter of NWCNT is about 5 to 10 nanometers, and sodium ion is only about 0.1 nanometers. So you can see that it can very easily intercalate and deintercalate. So this is a reaction which has been proposed. So you have the carbon coming from the nanotube, you have the sulfur which is used as an enhancer, and then we have the solvated sodium ion that forms a solvated complex during the sodiation. Sodiation means intercalation. And the solvated complex will dissociate during the desodiation or the deintercalation. So the reason why sodium has a very good affinity for carbon nanotubes is that it forms a stable bonding with the partially expanded multi-wall carbon nanotube, and it has got a negative binding energy, which shows that there is an attraction between the sodium ion and the carbon nanotube. So that makes it very easy for intercalation and deintercalation. So these are the CV curves and cycling behavior of the sodium device. So you can see that there is very good fidelity of the device. There is very little fade of the current voltage behavior. So we have actually varied the composition of the anode and cathode, and still we are able to get the same kind of non-fading behavior. So this is the high resolution SEM image of the cathode coating. So you can see that it is actually a composition which consists of carbon nanotubes, multi-wall carbon nanotubes bundle, and you can also see a single carbon nanotube which is appearing much larger because it is coated with the cellulose and activated carbon and sulfur. So this go and deposit on the walls of the carbon nanotube. Coming to the lithium ion chemistry, one of the devices we studied earlier was lithium sulfur battery. So the lithium sulfur battery was very attractive because it has got very high theoretical capacity and energy density. The capacity can be as high as 1640 milliampere hours per gram, and energy density can be as high as 2400 watt hours per kg. And the fabrication cost is quite less because sulfur is used, toxicity is less, and it has got a good safety profile and cycle life. So you can see some of the SEM images of the electrophoretic deposited carbon sulfur composite. So you can also see the EDAX analysis, which confirms the presence of sulfur. So we plotted the specific capacity in milliampere hours per gram versus the carbon to sulfur ratio. So you can see that there is an optimum ratio of about 1:1 when the specific capacity is the maximum. And we also carried out cycling studies up to 1000 cycles. So you can see that there is very good fidelity of the device with very little fade. So coming to another lithium ion chemistry, we studied lithium manganese oxide with graphene. This was a composite. So lithium manganese oxide and graphene was used as the working electrode. The electrolyte was lithium perchlorate and graphene was the counter electrode. And this was published in Energy Technology. So lithium manganese oxide is a promising electrode material because of low toxicity, low cost, and high abundance of the lithium and the manganese as well. So what we expected was high energy density and power density if you combine the lithium manganese oxide and graphene. So you can see some of the images. So this is the SEM image of the lithium manganese oxide and graphene composite in the ratio 1:1. And this is the discharge profile, the charging profile and the discharge profile. So we have actually varied the ratio of lithium manganese oxide and graphene. And you can see that the ratio 1:2 shows a very optimum behavior where you can almost see a flat profile, voltage profile, and then you also have a quick discharge. So this was taken as one of the better compositions for the device. This is a TM image of the composite where the graphene was coated on the lithium manganese oxide. So some of these devices were made using assembly unit, which is called supercapacitor assembly unit. So this has different subcomponents like cutting machine, then film coating machine, then you have a film applicator, you have hot rolling press, welding machine, and electrolyte filling machine. So this all comes in the single package. So coming to green energy storage materials, so what is meant by green? So green means something which is environmentally very friendly, right? So one of the recent work what is carried out was the construction of flexible and binder-free supercapacitive electrodes using nanocellulose, and this was extracted from areca nut husks, and then we combined it with polyaniline and silver nanoparticles. So we got a specific capacitance of 780 farad per gram, and we also got an energy density of 15.6 watt hour per kg and power density of 244 watt per kg. And the cycle life is also very good. It could retain up to 98% of its specific capacitance. This was published in RSC Advances. So this was the method for getting the nanocellulose from the areca nut. So you take the areca nut, you peel it, and then you do repeated acid and alkali treatment with HCl and NaOH. So you can shred the hemicellulose and you can also reduce the size. Then you carry out bleaching and homogenization. So bleaching was carried out using sodium diperchlorate, and then we also used acetic acid. So after the homogenization, we could get a stable sol, and we carried out XRD of the different subconstituents. So we carried out XRD of nanocellulose, then polyaniline, then silver polyaniline, then tani polyaniline and nanocellulose, and finally the composite. You can see the cyclic voltammetry and the charge discharge curves of the composite. This composite has silver, polyaniline, and nanocellulose. So you can see that the study was done at different scan rates and also for different current densities. An interesting thing was this was coated on copper foil. So as we know that copper foil is very flexible. The idea was to make a flexible device, and then you make the device and then bend it through various degrees. So we bend the device through 90 degrees, 180 degrees, and then we allowed some time for the device to recover, and then done the cyclic voltammetry as well as the charge discharge. So you can see that there is a considerable amount of recovery, right? So for example, if you bend to 90 degrees and 180 degrees, there is some reduction in the area under the curve. But upon recovery, it almost goes to the original area, right? So that the same thing is true for the charge discharge. So idea was to create flexible energy storage devices. And this shows the Ragon plot. Ragon plot is nothing but a plot of energy density versus power density. So this was plotted for the device, and it also shows the cycling stability. So you can see that the profile is almost flat, right? Up to 94% capacitance is retained. And then I would a little bit talk about some of the nano architectures for sensing, right? So this is in a way related to energy. It is not exactly into the supercapacitors, but I thought I can talk a little bit about this. So we made a sensing device which has carbon nanotubes and nanofluids, and this was a flow device. So we were able to get a very distinct voltage up to 4.1 millivolt, and this was due to the capillary rise of the fluid in the nanotube sensor. And this was done for different fluid systems, nanofluid systems, and characterization was also done with respect to the fluid system. And recently we have published in an Indian patent and also in the Taylor and Francis journal, which is Trans IMF, very recently. So this is the MW-CNT sensor, which was used for the flow device. This is the setup of the device, and this is the XRD pattern of the copper oxide nanofluids, nanoparticles. This is the device being used when the nanofluid is rising into the sensor. So you can see that the nanofluid is placed on the trough, and there is a channel-like device where the sensor is placed, and the fluid rises into the sensor using the Langmuir Blodgett effect or the capillary effect. And we also used some nano architectures for storage. So one of the things we thought was, instead of indium tin oxide for the touch screen, we can use graphene. So we have very different parameters of the graphene, such as, we have taken glass, then we have done some pre-cleaning. We have also varied the weight of graphene in the graphene ethanol suspension. We have used adhesion promoter such as polymethyl methacrylate, and we have found some optimum parameters, which are nothing but longer cleaning times, lower graphene weight, and the use of PMMA. And we have studied different characteristics such as optical transparency, adhesion, electrical resistivity, and some modeling was also done. So this was also recently published. So this shows, the resistance, contact resistance of the graphene coated device for different times of pre-cleaning. So you can see that the sample with the nomenclature 1/4S1P has got some of the lowest resistance, right? Among the other samples prepared, this has got a resistance as low as 1.05 kilo ohms. So this was taken up for further study. We have done some addition tests which are based on ASTM. So these are called as expert method. So we have taken the sample after preparation, we have done an expert, then we have done a peel off. So this is done for two types of samples. So you can see that some of the samples they retain significant amount of the coating even after peel off. So that shows a very good addition of the coating to the glass. And we have done some modeling primarily on the optical properties. So the left-hand side shows the refractive index behavior versus thickness, and the right-hand side graph shows the electrical behavior with respect to thickness. So what we have found is there is an optimum layer thickness for which the refractive index or properties are a maximum. And for other layer thickness, the refractive index values are lower. But what we require for optical transparency is that the medium should have lower refractive index. And similar trends were observed for electric field. So what we have found is electric field is lower as the sample thickness or number of layers increases. So if you combine these two, they are somewhat contradictory. So there is some optimization or meeting point. So what we have concluded is, the lower layer thickness is better for glass graphene layers for the touch screen with higher optical transparency and high electric charge. And I also worked on solar nano perovskite materials for storage integration. So one of the compounds we chose was cesium sodium bismuth. This is used in the perovskite solar cells as a photoactive layer. And we have been able to synthesize the perovskite compound with high purity, which is more than 98%. So purity is very important in the perovskite because the current generated from the solar cell, if you have impurities, they will contribute to the recombination process, and that will reduce the electron and hole density, and effectively the cell will not perform as well. So we have changed some of the filtration and cleaning processes and improved the purity to 98.45. And we also some solar cells were made and IV curves characterized. So this is an Indian patent very recently. So this is the XRD graph of the 98.4% pure perovskite. So this is also, once the patent is granted, we'll be publishing it. So this is a brief about my past and current research work, which has been touched upon many systems. As I told you, I worked upon integrated storage. I also worked upon conducting polymer storage, graphene storage. Then I worked upon sodium-ion batteries, lithium-ion batteries. Then I also worked upon the sensors, carbon nanotube sensors, carbon nanotube graphene storage. So that gives you a glimpse of the different aspects I have studied over the last 14 years. So coming to the IP and the product development, many of these works are protected by patents, and I have also done some product development in the areas of integrated storage, flow sensors, sodium batteries, and solar nanomaterials. And most of our patents are flowing into we have a Ramaiah Evolute incubation cell. So which actually embraces this patent and tries for startups and innovation incubation. So what are the challenges in IP creation? From my experience, I can just put down a few points which may be useful when you as researchers go for IP generation and creation. So one should have an absolutely innovative idea, which is backed with initial data. So that is a starting point for applying for a patent. And one should do some prior art search before submitting a formal IP application. So you should see, how your patent application stands out. And one should mention all the details in the full specification and follow up. The first step is filing, then you have examination, and finally you have the granting of the patent. So you should follow up till the end. And once the patent is granted, you can tie up with premium industries for commercial prospects, and also taking into account the royalty which is due to the institute and the patentee. So these are some of the things to be kept in mind, especially when most of the work involves innovative ideas, which has to be protected. So I come to the concluding remarks. The current energy storage trends are moving towards high areal density and stable devices on flexible substrates. And researchers are also looking at advanced electrochemical characterization. They are also studying novel and innovative concepts and materials. And nowadays, researchers are very much, keen on IP creation and commercialization. So whatever research we are undertaking should be geared to the above points. If you are able to tune the research, taking into account the above points, then it will be more useful and more productive. So with that, I come to the end of my talk. I hope, Professor Dinesh, that I have not exceeded my timeline.
No, on time. Thank you, sir.
Yeah. So I think that is the end of my
take some. Yes.
Yeah. I just acknowledge my various collaborators, mentors, and PhD, my students. So these are various people who have worked with me, and all this. Open for the question session, and thank you very much for your time. And I hope to take some questions and answer them.
Yeah, thank you. Thank you for your talk. You can unshare your screen if you want.
Okay.
So there are few questions we have.
Yeah.
Can you please explain how the synthesized nanomaterials storing this energy for all the models that you are explaining?
Yeah, for example, like if I take the very first thing what I explained, the integrated solar and storage. So what we do is we take a titanium plate and then we anodize the titanium plate. So anodization is a very simple electrochemical process where you take the plate and you dip it in a suitable chemical, and then you apply a voltage. So what happens is certain pits are formed on the plate due to the difference in current density, and that leads to the growth of the nanotubes in one direction. So that is how the nanotubes were formed. And double anodization is a special technique which is actually, we have fine-tuned the anodization parameters. So that is how we were able to achieve anodization on both sides of the titanium plate. And coming to the yeah, there are some questions also. I think I am getting some questions on the screen. Shall I answer them, or shall I go take it sequentially?
We will take it sequentially. I am asking a question for what Guru Prasad Gurtala has asked.
Okay, fine, yeah. So coming to the polypyrrole, polypyrrole is a connecting polymer. So, there is something called electropolymerization. Now, polypyrrole can be formed in two ways. One is natural polymerization or chemical polymerization, and other one is electropolymerization. So, if you do natural polymerization, you have to take pyrrole, which is the monomer. Then you have to add a polymerizing agent, and then it will become polypyrrole. The other way is you take polypyrrole neat solution, and then you do electropolymerization, which means you actually apply a voltage in a suitable solvent, and then the polymer fibrils, they grow naturally. So that is how we were able to get those nanofibrils of the polypyrrole. And electrophoretic deposition is again a electrochemical technique where we take the solution which contains the material to be deposited. For example, if you want to deposit graphene, you have to have a solution of graphene and ethanol, or graphene and isopropanol, and then you have to add a charging agent which is nickel nitrate. So that will help in the the migration of the graphene nanoparticles towards the cathode. And the anode used is a platinum wire, right? So that is how you do the electrophoretic deposition. And then if I take another material like say cobalt hydroxide, I told you that again it is electrostatic galvanostatic deposition, starting from cobalt chloride, right? So that is how you deposit cobalt hydroxide nanoflakes. And then the other material is sodium battery. So that is, what we do is we take the individual constituents like, the multi-wall carbon nanotubes, sulfur, then activated carbon, cellulose, and we do a ball milling to homogenize constituents. And then after that, we coat it on the substrate. And, we also do some post-processing of the nano layer, which is coated on the substrate, before we actually make the electrochemical cell. And then coming to the lithium ion chemistry, I have talked about lithium sulfur. So that is again the electrophoretic deposition of activated carbon and sulfur. And lithium manganese oxide and graphene were also deposited by electrophoretic deposition. But nowadays there are some scaled up techniques which are available, like screen printing. That is one of the scaled up techniques where you can deposit these layers over large areas. So if one is looking at scaled up devices, then we have to go for the newer techniques. So I hope I have given the kind of techniques which are used in the synthesis of these materials.
Thank you. Thank you, Professor. So the next question is related to which type of PV cell is the best for concentrating PV technology? Hello?
Yeah, am I audible?
Yeah, you're audible now.
Yeah,
So
can
the
you
next question I will repeat. Which type of PV cell is the best for concentrating PV technology?
Yeah,
This is
so
by
PV
Professor Arun Sharma.
yeah, PV cell is different and concentrating PV technology is different. So what I mean is photovoltaics, that has different types of cells like silicon. One can also use, the dye-sensitized solar cell or quantum dot sensitized solar cell. So wherein, the main principle is that once the solar light shines on the active material, you have a separation of charge carriers. And then, one type of charge carrier is taken in by an electron accepting layer, and the other type of charge carrier is taken in by a hole accepting layer. And that is how the charges are separated, and that leads to an external current. So that is how photovoltaic materials work. Whereas if you take materials for solar concentration, then we have to look at, how to absorb the solar heat. Whereas because in the concentrating kind of architectures, the solar heat is more important. So we have to look at systems like nanofluids, or we have to look at systems like molten salts, which can absorb the solar heat effectively and then convert to the heat energy which can be stored. So both systems are different. The principle of working is different.
Okay, thank you, sir. So the next question is basically recently which materials gives higher hydrogen storage capacity? I think Professor Nivedita.
Yeah. So I
Your
think people are looking at core shell technologies nowadays. So one of the most interesting materials is magnesium hydride, MgH2, or magnesium borohydride, where actually it is made in the form of a core shell, and even the hydrogen storing and hydrogen extraction is part of the same architecture. So these are some of the latest materials which are being currently explored.
Okay. Professor Nivedita, you want to talk? Want to have some follow-up question? You raised some hand. Professor Nivedita?
Hello.
Huh.
Dheeraj sir, I have posted a question. Probably you are not able to locate. It's in the message box.
Yes, yes.
Yeah, yeah. She has said no, no, I think. She has said no, actually.
எதுல கனெக்ட் பண்ணேன் இல்ல சார் பேண்ட் வித் நோஸ்ன்னு போட்டேன் மெசேஜ்
Okay. So we can go to the next question by Professor Prashant Revankar.
Yeah.
Professor Prashant Revankar?
Sir, I just wanted to know about the sustainability aspects of using nanomaterials from the perspective of their manufacture and the final disposal of the materials.
Yeah.
Would you just throw light on any specific case studies which justify that they are safe in use and they are sustainable?
Yes, sir. So actually, if you look at the sustainability, some of these nanomaterials, of course, they are toxic. So mostly the research level, we work with materials that low concentration. So that much of an extent.
Hello. Professor Revankar, am I audible?
Yes, sir. Yes, sir.
I think he has lost the connection again.
Yes. Thank you, sir. Thank you.
We'll take Professor Arunachala's question. Hello, Professor
Yeah.
Subramanian.
And then the connection got.
Yes, thank you. So we have Professor Arunachala.
Yeah.
He has raised his hand.
Okay. Yeah. Yes, sir.
Hello, hello, Professor. Am I audible?
Yeah, you are audible.
Yeah, thanks. So my question is about solar PV concentrated technology, not thermal concentration.
Okay.
So for concentrated PV technology, since the temperature, working temperature is a bit high,
Yeah, right.
despite of efficient cooling system,
Yes.
in that case, this poly or monocrystalline cell may lose its property or it may get damaged. So
Correct.
in that
Yeah.
case, what I heard was about multi-junction solar cells.
Yeah, right.
On that basis, I'm asking: is there any kind of that kind of material or the kind of photovoltaic module is available as far as India is concerned? That's what.
Yes, sir. Actually, the multi-junction technology is a bit expensive because we are looking at semiconductor thin layers. So we are looking at forming quantum well junctions or where the charges can be stored or trapped. So people are trying to move away from that, and they are looking at technologies which are based on quantum dots. So, for example, many of the semiconductor materials can be made into quantum dots, which have excellent properties of quantum confinement, and they can be very well used for, they are also photoactive, so they can be used for the charge storage and charge transfer. So that is much better than the conventional materials which cannot withstand the high solar heat.
Okay. Okay. Thank you.
Thank you.
Thank you, sir. So there are further couple of questions.
Okay.
So what is the difference or challenges you see in flow batteries versus flow capacitors?
Yeah, so flow batteries is a very well established area now because we have vanadium redox batteries, and we have even other kind of rare earth materials which are used. But flow capacitors, the main challenges in formulating the slurry. Because the slurry makes a lot of difference in the kind of energy density you get or the power density you get, and also the volumetric capacitance. So, for example, the slurry what we made for our capacitor, it had nearly about 10 constituents. So we made in-house graphene by ball milling, and then we had oleic acid, and then we added some more surfactants, and then we added enhancer. So it is not that easy to make the slurry, because ultimately the slurry will decide. I mean, the other things can be made like the flow container and the peristatic pumps and all that can be made, but the slurry will decide the performance of the device. So it is not that easy to make the slurry.
Sure, thank you. How to combat swelling effect of polymer in lithium-ion polymer batteries? Swelling effect.
So that is a major problem because many of these polymeric systems, they show the swelling, and that is also the reason for the degradation. When you run it to a large number of cycles. So the main thing is one of the ways of reducing the swelling is if you can actually make composites. So, for example, if you have a dispersion of stable materials like oxides or inorganic oxides in the polymer in a higher volume fraction, then to that extent the swelling of the polymer can be reduced because of the constraints imposed by the inorganic constituents. So the key is to make the composites in a sufficiently high volume fraction so that the swelling effect can be reduced.
Okay, thank you, sir. So may I invite Dr. Nivedita? So she is asking a question regarding, yeah, please.
Yeah.
Yes. Hello, sir. I am audible.
Yes, madam. Yeah.
Sir, in hydrogen technology, which material is the latest material in metal hydride, sir?
People are looking at magnesium hydride. Magnesium, not just MgH2, but a composite of magnesium and other elements.
Sir, titanium and carbon incorporated materials nowadays using, sir?
Titanium and carbon also shows the hydrogen storage property, but one of the problems is that hydrogen embrittlement.
Okay, sir.
So that is why, people are trying to get materials which have a greater crack resistance in hydrogen embrittlement.
Okay, sir. Thank you, sir.
Thank you.
Thanks.
Thank you.
Thank you. So we came to the end of this question answer session.
Yeah, sir.
So I'd like to thank you, Professor Subramanian, for the talk and the
Yeah.
audience for question answer sessions.
Yeah.
We would like to thank the all of you for spending your invaluable time for this talk session. So we will look forward for your participation in talk 15, this talk 15, that would be in the second week of October. We will send out the information about the same. Thank you all for joining. Thank you, Professor Subramanian.
Professor Dheeraj, I also thank you very much again for the invitation, and I again thank my management and also IIT Dharwad for giving me the opportunity. So let us hope we can interact more, and we can collaborate on many areas.
Definitely, sir. Definitely. Yes. Thank you. Thank you, Banapramat, sir.
Thank you.
Thank you.